Hello again, my name is Tom Irvine and I'm the instructor for this series of shock and vibration webinars. And today we're going to be continuing with shock, and we're going to be talking about seismic shock. Now, an important point I want to make right off the bat is that some of you, for example, deal with pyrotechnic shock, and we will be covering that in the next webinar after this one. But really, the principles that we're going to learn today apply just as well to pyrotechnic shock as they do to seismic shock. The big difference being that the pyrotechnic shock is a high-frequency event, whereas with seismic shock, the energy occurs at very low frequencies. So we're going to start off with a historical earthquake, and this is the El Centro or Imperial Valley earthquake in 1940. And this earthquake's important to us because it is the first earthquake for which valid, quality, accurate, strong motion engineering data was measured. So strong motion, I'm referring to the ground motion. So the right instrumentation was in place to make that recording. 9 people, sadly, were killed by this earthquake in May of 1940. And another interesting point is 1940 was a very important year for shock and vibration, and this has nothing to do with World War II, but rather the two important events were this El Centro earthquake as well as the Tacoma Narrows Bridge failure, which happened several months later. So at the Imperial location, 80% of the buildings were damaged to some degree. In the business district of Brawley, all structures were damaged and about 50% had to be condemned. The shock caused 40 miles of surface faulting on the Imperial Fault, which is part of the San Andreas system in Southern California. Total damage has been estimated at about $6 million, and the magnitude was 7.1. So here's an acceleration time history measured from this earthquake event, and this was the north-south component, so it's parallel to the ground, and we see acceleration in g's versus time in seconds. And as you look at that amplitude, the amplitude is less than 0.4 g, so you might think, well, that's a very negligibly low or benign amplitude, but this is occurring at a very low frequency. You see this signal stretches out to over 50 seconds. So there's a lot of low frequency energy there, and that creates high displacements. So this is a concern, and it does have a severe damage potentials for buildings and bridges and those types of structures. Another thing I want you to notice, if you disregard the numbers along the y-axis and the x-axis, if you just look at the shock pulse, this could almost be a pyrotechnic shock measured at, say, a mid or far field location, some distance from the source. So what we're doing again, what we're going to be doing in this unit today, the principles are valid for pyrotechnic shock or seismic shock or any type of other shock event as well. So here's our familiar single degree of freedom system that we've discussed so many times in this course. So we have the mass M, we have the spring stiffness K, and we have the damper or dashpot with the viscous damping coefficient C. We've got a base input, that's y double dot, that's the base acceleration. Then we have the response acceleration x double dot. So x double dot is the absolute acceleration of that mass. Now, we've talked about the process in previous units of going through, and we have to set up a free body diagram and use Newton's laws and derive a governing differential equation of motion. And if our base excitation function is something well behaved, like a sine input or a half sine input, then we can use Laplace transforms to readily solve that problem and get an exact answer. Well, today we're talking about functions which can vary arbitrarily with time. And in this case, in order to solve that second-order ordinary differential equation, we need to use something called a convolution integral, or some people might call it a Duhamel's integral. And we've actually talked about this before in previous units. Well, it turns out that convolution integral is very inefficient to solve, so instead we transform it into a digital recursive filtering relationship, and this makes the calculation go much more quickly. So what we use is, well, David O. Smallwood, he worked at Sandia Labs for many years before retiring or semi-retiring, and in a paper long ago he came up with I'll call it the Smallwood ramp invariant digital recursive filtering relationship. And again, we've seen this before. We've used it before in previous units. For example, we took white noise as a base input and applied this equation. Well, again, we're using the same equation, only we're using it for a short duration transient shock pulses in this unit. So anyways, the absolute acceleration of that mass is equal to these 5 terms here. And the first 2 terms on the right-hand side of the equal sign are the recursive terms. So you could think about this in terms of a filter. This is like a feedback loop. So this equation solves for the absolute acceleration of the mass at index I, that's the time index, plus this coefficient times the absolute acceleration 1 time step ago, minus this coefficient times the absolute acceleration 2 times steps ago. Again, these 2 terms make up the recursive part of the equation. Then we have 3 terms here, and we have this coefficient here times the base acceleration at time step I, plus this coefficient here times the base acceleration 1 time step ago, plus this very long coefficient here times the base acceleration at 2 time steps ago. So this equation, it's reasonably straightforward to program it into MATLAB, and it allows us to calculate the absolute acceleration of that mass. And there's also a similar type of equation that we can derive for the case of the relative displacement. And that's available in some of the papers I posted on my blog. So let's go ahead and do an exercise with our MATLAB script. We're more concerned here with application than theory. You can get the theory from the papers on my blog or website. So we're going to actually run a program we've run before, and this is vibration data underscore SDOF underscore base.m. And this script calculates the response of a single degree of freedom system to a base excitation where the input data must have 2 columns, time in seconds, and then the base acceleration. And we're going to use that El Centro earthquake data for the north-south ground component. And we'll do the case for a natural frequency of 1.8 hertz with a Q value of 10. And for the purpose of this exercise, this is just a point that I've just kind of arbitrarily chosen. So if you had a building or a bridge or some structure and you knew the natural frequency of that structure, then you would just substitute in the appropriate natural frequency. So just for today, let's assume that we have a building and it has a natural frequency of 1.8 hertz. So let's go to vibration data, to our main GUI package. Okay, it takes a moment. So this week we're up to version 5.6, and as I like to say, and rising. So we're going to have a time history input. That's going to be the El Centro north-south component data. We're going to do a single degree of freedom response to base input. And let's see. So here we are, and this was You've already seen the screenshot of this in the slide. Plus, we've run this particular function before in past units. So we're going to have our input. It'll be an external ASCII file. So El Centro underscore ns.dat, that's the north-south component. We'll have English units. And just for our hypothetical building that has a natural frequency of 1.8 hertz, we'll type in that frequency and let's calculate what the responses will be. So I get a couple of things here. One thing, just to make note of, we do get a summary of the important statistics in this box here, so you can see for both acceleration, this is the response acceleration g, and the relative displacement in inches of the various max and min values, as well as the RMS and the crest factor. So here's our base input acceleration. So this is from the measured data from the 1940 El Centro earthquake, north-south component measured on the ground, acceleration g versus time in seconds. And we've actually seen this before in the PowerPoint slide. So here's our acceleration. I think I'll put let me switch these plots around. Base input on the left, response on the right. So we have our acceleration response, 1.8 hertz, q is equal to 10. And you can see the scales are different here. So our response in this case, our peak response is about 0.9 g, whereas our peak base input was about 0.35 g. So we are getting a dynamic amplification effect at 1.8 hertz. And if we look at this data here just sort of qualitatively, it looks like at least the frequency content is somewhat sinusoidal. And if we did the method whereby we count the peaks and divide by time, that should come out to be about 1.8 hertz. But the amplitude itself is in sort of a damped transient way, is varying arbitrarily with time. Although you can see the effect of the damping, or you could say the exponential decay going on. So these two plots would be useful for us if we were trying to design a building with a natural frequency of 1.8 hertz that needed to withstand the El Centro earthquake. Well, there's one more plot that's also of concern, and this is the relative displacement. So relative displacement, inches, versus time in seconds. And our relative deflection or displacement, it looks like, well, let's just go back and look at the descriptive statistics. Oops. Okay. Got too many things going on at once here. Let's go back to our command window. And where did our command window go? Our GUI, I should say. Okay, the relative displacement, the peak and absolute value was 2.7 inches. So that is a fairly high displacement, and if we're concerned about the foundation of the building, we need to have a foundation that can withstand that relative displacement. Of course, we're modeling the whole building at this point just as a spring mass single degree of freedom system, and if we were doing this in earnest, we'd probably have a finite element model of that building. But you get the idea. This is just sort of good for a kind of a quick look at what's going on here. So let's see what else we want to do with this. Go back to the slides here briefly. So here's the 1.8 hertz Q is equal to 10 single degree of freedom response. I've demonstrated how to generate this plot. And of course, everything we're doing today in this unit, I'd like you to go and repeat as a homework exercise. Okay, here's the relative displacement response with its natural frequency, 1.8 hertz again, Q is equal to 10. And you've seen this plot before. Looks like I rounded up a little bit, and the peak relative response I'm calling 2.8 inches. Okay, there's another parameter that's going to come into play here, and there was a fine gentleman, an engineer by the name of Dr. Howard Gaberson. He's passed away, but I did have a chance to meet him on 2 occasions. And he wrote a series of papers and really championed the idea that dynamic stress is proportional to well, it's actually dynamic stress is proportional to pseudo velocity. So I need to change that slide here. But in order to calculate the pseudo velocity, we need to calculate what the relative displacement is. So this is a tad embarrassing, but I'm going to change the slide as I speak. Okay, let's fix that. That just doesn't look right, does it? There we go. Sometimes I make mistakes. Okay, fix that. But anyways, the pseudo velocity, PV, it's equal to the natural frequency, or you might say the angular natural frequency in radians per second times the relative displacement. And this is how we would calculate a pseudo velocity. And as we go on in the upcoming webinars, we're going to talk about how there's certain severity thresholds for shock testing that are represented in terms of the pseudo velocity. And we'll talk a little bit more about pseudo velocity within the slides within this unit today as well. So there's something called a amplitude Srs amplitude conversion that's within the. Okay, let's note here, for example, that we have our peak G level is going to be about 0.92 G, and our relative displacement, it looks like I got a little bit off with my rounding off. It's 2.747 there in terms of absolute, or I guess if you just want to throw on some conservatism, call it 2.8 inches. But let's go to vibration data. And if we go to our amplitude conversion utilities, we're going to do SRS amplitude conversion. So we've got our English units, we'll just the first choice now in that list box. So let's just play around. Our absolute acceleration, and this is our response acceleration, was 0.92 g at 1.8 hertz. So what's the corresponding relative displacement? What's the corresponding pseudo velocity? So you can see at 1.8 hertz, the peak relative displacement is about 2.8 inches. The pseudo velocity is 31.4 inches per second. And the acceleration, which we input, is 0.92 g. So these set of three amplitude metrics and with the accompanying frequency are all consistent with one another. So for the purpose of design and analysis work, we need to be aware of each of those three metrics. Okay, and we can also just do other things. What if we wanted to input the relative displacement? It'll be at the same natural frequency, and I'll just put our rounded up value of 2.8 inches. And we get the same, really the same set of numbers again. Again, we're at 1.8 hertz, relative displacement 2.8 inches. That was a given. Corresponding pseudo velocity almost 32 inches per second, and the acceleration 0.92 g if we just truncate to 2 decimal places. So that's just sort of going back and forth, calculating amongst those three metrics, with the pseudo velocity being calculated from the relative displacement. And these are all kind of approximate relationships anyways. And if we wanted to get the relationship between the absolute acceleration and the relative displacement, so let's say we have A for absolute acceleration on this left-hand side, that would be equal to omega squared times the relative displacement. And I've got a paper I'll post that goes over this on my blog, that goes over these relationships in a little more detail along with their derivations. Okay, so we did our SRS amplitude conversion. Okay, now we're going to run a new program, and we're going to calculate a shock response spectrum for the Centro earthquake. So last week we did shock response spectrum for half sine pulses. Well, today we have a pulse that varies arbitrarily with time, so it's going to be a time history input, a shock response spectrum. Let's calculate. We've got our external ASCII file. That's the El Centro north-south component. English units. Now, since this is earthquake data, we're going to start at 1/10 of a hertz, and we'll go up to 20 hertz here. Those will be our plot limits. So if you're familiar with pyrotechnic shock, and that's what you work with, just imagine your pyrotechnic shock energy transposed down to very low frequencies. But this is the El Centro earthquake. So I hit the calculation button there. And let's see what happened. Okay, I get a series of plots that come up. A whole bunch of plots going on. And we need to look at these maybe in order, I guess. So this plot here, you've seen it before. This is just the ground motion in the north-south axis. Acceleration g versus time in second, and that's our base input. You've seen it before a couple times. Okay, here we get a shock response spectrum, and I'm calling it acceleration SRS, Q is equal to 10. Now please, anytime you generate a shock response spectrum, please put the Q value in the title, or if you'd prefer, put the viscous damping ratio. So this is Q is equal to 10. So I could have also said 5% damping, and that would have been okay. But please do one or the other. The Q value is a little more conventional of the two. Either is fine, but please do one or the other. Along the y-axis, we have peak acceleration. Along the x-axis, we have natural frequency in hertz. And this is another point that I'm very particular about. It's a pet peeve. Do not simply say frequency in hertz. Rather, this is the natural frequency in hertz. There is an important distinction there, because this is the response of the single degree of freedom oscillators. Now, 1.8 hertz, remember we had that 1.8 hertz, and it was about 0.92 G. Well, that's the point right there. We did our own time domain calculation and found that out already. Well, here's that point showing up on the SRS plot. So these two SRS curves for positive and negative, we could have manually generated these curves by going at each natural frequency with some fraction of an octave spacing or whatever. And we could have gone frequency by frequency, picked off the peak values and plotted them and generated these curves. Well, the SRS program that we just ran does all that bookkeeping for us. So it goes through the response time domain calculation, records the peak positive and peak negative values, and then discards the rest of the response time history for each natural frequency. So there we are at 1.8 hertz, which is the x. We have the y, which is 0.92 G's, peak acceleration. Now, as we look at these two curves here, this is giving us a hint for design purposes. And that hint is, if we want to minimize the absolute acceleration of that building, or maybe a piece of equipment in that building, or some structure, whatever we might have, we should have the least possible natural frequency. Because the lower the natural frequency, the more isolated our system is, and we essentially attenuate the acceleration and achieve a very desired result of minimizing the response acceleration. Well, that's all well and good if acceleration is the only thing we're concerned about, but it's not. So let's say we got a couple other plots going on here. On the left-hand side, I've got relative displacement, again, SRS, noting Q is equal to 10. You have the peak relative displacement in inches and the natural frequency in hertz. And here are the two curves, positive and negative. Well, in this case, the lower our natural frequency, the higher our peak acceleration. Excuse me, our peak relative. Let me start over. The lower our natural frequency, the higher our peak relative displacement. So if we went down to a tenth of a hertz, then we have a negligibly low response acceleration, but our peak relative displacement is maybe 12 or 13 or so inches, and that would most likely be too much. So if we want to minimize our relative displacement, then we should have our natural frequency as high as possible. So if we go out here, this is in terms of design work. So if we go out here, this is effectively hard mounting our system in relative terms. Or on this acceleration plot, if we go down here, we're isolating our system. Well, it's okay to isolate, but we need to make sure that our spring can withstand the corresponding relative deflection. So what's the correct answer, the so-called correct answer? Obviously, it depends. It might be some moderate frequency, some intermediate frequency, natural frequency, in other words, might be the best choice. Well, there's a third plot, and this is the pseudo velocity SRS. So we have our peak velocity in inches per second, natural frequency in hertz. And in this case, the pseudo velocity is calculated by taking these two relative displacement SRS curves and going point by point and multiplying by omega sub n, where omega sub n is 2 pi times the natural frequency in hertz. And again, if we go back to the work of Howard Gaberson and others, they claim, Gaberson and his colleagues claim, that stress and damage have a better correlation with pseudo velocity than either with relative displacement or with acceleration in g's. Obviously, there's exceptions to that to their claim, but it's still a pretty good claim. And another reason the pseudo velocity is often favored is that it takes typically, not always, but typically, it takes less decade space along the y-axis to represent the pseudo velocity. So you can see here these two curves. If we were to shift these curves downward to the bottom, these two curves take less than 1 decade along the y-axis to represent. Whereas with both relative displacement and pseudo velocity, both relative displacement and acceleration, it takes about 2 full decades to represent each of those curves. Now, if we turn this into a linear plot, you'd see there'd be, for the pseudo velocity, there would be quite a bit of peak-to-peak or point-to-point variation, but relatively speaking, and I'm using the term relatively very loosely, but relatively speaking, the pseudo velocity tends to remain more stable as the natural frequency changes. That's not perfectly true, but it is relatively true compared to relative displacement as well as to to absolute acceleration. So if we have, particularly in this region, if we have changes in natural frequency, there are large changes in relative displacement, and particularly in this natural frequency domain here, the absolute acceleration response changes rapidly with natural frequency, whereas with pseudo velocity, the two curves tend to remain more stable. And I'm using the word tend somewhat loosely there. So that's another reason that civil engineers and Howard Gaberson and others like the pseudo velocity representation. And again, we're going to be talking about some empirical severity thresholds in terms of pseudo velocity in some upcoming units. Okay, let's see. We actually have one more plot, and this is a fun one. It might give you a headache the first time you look at it. And Howard Gaberson, if he were here, he would call this 4-coordinate plot, or 4CP. That term is perfectly acceptable to me. If you like to call it that, that's perfectly fine. I tend to call us by another term, and that's a tripartite plot. Either way is fine. So primarily what we're representing is our pseudo velocity shock response spectrum, Q is equal to 10, where we have velocity in inches per second, that's along the y-axis, natural frequency in hertz along the x-axis. So if you ignore all the diagonal lines, you've seen this pair of curves before. But here's the difference now, is if we take the downward sloping lines, this represents the equivalent acceleration in g's. So this downward sloping line is 1/10 of a g, and this downward sloping line is 1 g. And this particular point here at 1.8 hertz, we're going to pick up, let's see if, okay, there we go. So at about 1.8 hertz, we have about 31 or so inches per second. And if we tilt our head and sort of squint our eyes a bit, it turns out that that point is just about 0.9 g. And that's something we already realized from our prior calculations for this very natural frequency. So we're getting, so far we're getting two pieces of information off of this plot for the frequency, natural frequency of 1.8 hertz, and that's the pseudo velocity of 31 inches per second and the acceleration of 0.9 g. Well, wait, there's more. And that is if we tilt our head 90 degrees the other way and look at the upward diagonal lines, these are our relative deflection diagonal lines. So this one here, upward sloping, is 1 inch. Then this one here, upward sloping, is 10 inch. So if we kind of can sort out all these different lines here, it looks like that we are getting a relative displacement at 1.8 hertz of about 2.8 inches. Again, that's the relative displacement. So those are the three amplitude metrics occurring at 1.8 hertz. And you recall earlier we looked at that little function within the vibration data MATLAB GUI package where we did our SRS amplitude, and we typed in 1.8 hertz, and we typed in 0.92 Gs, and we were able to calculate the three equivalent amplitude metrics for that frequency of 1.8 hertz. So these are just different tools, and it's nice to have a whole set of tools in our toolbox, and depending on what you're doing, one format might be better than another. If you just have an avionics box or a piece of equipment, maybe all you really need is the acceleration SRS, or if you're trying to compare against some shock severity thresholds, you're more interested in the pseudo velocity SRS, or if you're looking at the spring or ice layer deflection, you might be particularly interested in the relative displacement SRS. Or you can look at all the metrics together in this jumbled up 4-coordinate plot, or as I call it, a tripartite plot. So these are just sort of fun tools to use, and I hope you can make good use of them. Well, let's think about something else. This is the El Centro earthquake, 1940, north-south component. And let's say that we have to come up with an equivalent static load for, say, bridges in California to withstand a El Centro class earthquake. And it's going to be an equivalent static acceleration in g. Now, that whole phrase, by the way, causes me to squirm. I'm very uncomfortable about it. There is no such thing as static acceleration. Maybe there's quasi-static acceleration, but the idea is that we would pass an equivalent static acceleration value off to the structural or stress analysis engineers, and they would run a static analysis within finite element modeling in order to determine whether their structure could withstand that so-called equivalent static load. Well, that's kind of sort of okay. It would be much better if they did a modal transient analysis in the time domain, but it's just sort of the convention that we're in, that we find ourselves in, that we're duty bound to pass along just a single equivalent to static acceleration, which could then be applied as a body load in that static finite element model. Okay, so what acceleration would we then use for the for these hypothetical bridge structures to be constructed in California? Well, it looks like our peak accelerations are, there's 2 points that we just go a little bit above the 0.9 g, and just for conservatism, let's round off to 1 g. So we might say that 1 g is the equivalent body load that we need to pass on to our the static structural engineers. But we like to add a safety margin. That's very typical. Or you could call it a statistical uncertainty factor or whatever. So let's add on 6 dB. And if we do that, that's going to double our 1G level to 2Gs. And then 2G would be the numbers that we would pass on to our structural engineer colleagues. So does that seem reasonable, 2Gs, for a so-called equivalent static load? Okay, just kind of put that thought in the back of your head for now. So these are the slides. We've already seen this, these set of slides before. That's for our Centro earthquake, relative displacement SRS, corresponding pseudo velocity SRS, which is calculated from the relative displacement SRS. We have our acceleration SRS. So these couple of points here, just barely exceeding the 0.9 G line. So again, we rounded off to 1 G, and then we added 6 dB margin to get to 2 G. Oh, and then here was our tripartite or four-coordinate plot SRS. And here I'm pointing out that point that we focused on at 1.8 Hertz for our hypothetical building structure, and then the corresponding and consistent set of amplitude metrics there. Okay, so here we go. We can tie some things together. Now, one of the very first webinars, maybe in fact it was the first one, we talked about natural frequencies of structures. Well, Caltrans, that's the California Department of Transportation, has a standard that requires bridges to withstand an equivalent static earthquake force, EQ, of 2.0 Gs. Where did that come from? Well, to be honest, I don't know for sure, but I think it's highly plausible that that's based, at least in part, on that El Centro SRS peak acceleration with a statistical margin of 6 dB. And that certainly makes a good story, and it seems very likely. But maybe it's a homework exercise. You can fact check me on that one. Just a couple other, we're going to have some closing slides here. This is mostly just going to be fun stuff here. So some of you maybe work for NASA or some aerospace company, and you're involved with launch vehicles. So why would you be interested in earthquakes? Well, here's Vandenberg, California, and this is a typical launch vehicle. It happens to be a SpaceX Falcon type vehicle. And Vandenberg, California, that's located not too far from the San Andreas Fault. Now, it's very unlikely, highly unlikely, that in, say, the 2-week period, I'm just throwing out 2 week as a rough estimate, that 2-week interval where that launch vehicle is mounted on the pad prior to launch, it's highly unlikely that an earthquake event would happen during that duration. But you have to remember that depending on the launch vehicle, depending on its payload, that could be $1 billion. So here we have this launch vehicle. It's like a tall cantilever beam mounted to the ground. So if the ground starts shaking, that's going to excite the bending modes of that vehicle and could overstress the joints or the payload or cause something else bad to happen. So there is a NASA handbook. It's 7005 that actually gives a shock response spectrum for typical Central California earthquakes. So we have acceleration G along the y-axis. We have the natural frequency in hertz along the x-axis. And in this case, we have a family of 3 curves with the respective damping values. These are, you could call these the viscous damping ratios or the modal damping ratios. So depending on what the damping is, then we can pick off what the appropriate SRS curve is. Well, hopefully we also know what the natural frequency of our launch vehicle is. And typically for launch vehicles, of course, it depends on mass properties and the height of the vehicle and those sorts of properties, joint stiffness and so on. But we might expect that when it's mounted on the pad to be somewhere between 1 to 2 to 3 hertz. So then for the appropriate damping for our vehicle, which hopefully we also know, we could pick off what the peak acceleration in G would be. Now this dashed line here, it says peak acceleration of the earthquake, and this is the peak ground motion. But what these solid curves are showing are the peak absolute acceleration response. Of course, we're modeling this whole launch vehicle as a single degree of freedom system, and that's okay just as a first cut at the problem. But probably what we would want to do is go back and do maybe synthesize a time history to satisfy these SRS curves and do a modal transient analysis. And in an upcoming webinar unit, we're going to be in fact doing that, synthesizing time histories to satisfy SRS specifications. Or we could just take that El Centro time history, which we have in ASCII text format that we've already taken a look at, and we could use that to base drive our launch vehicle for a finite element modal transient analysis. And that would be better because we'll be modeling the launch vehicle as continuous systems, at least as best we could with nodes and elements. And we could account for the fact that there's several modes that could be excited. But even if you're just working for NASA, you should be interested in earthquakes. Just kind of a few fun things here. Just a couple of historical earthquakes, mostly in the United States. The most expensive earthquake in recorded U.S. history was the 1906 San Francisco quake. This occurred 5:12 a.m. on April 18th, 1906, and the source was a rupture of the San Andreas Fault. The severe shaking duration was about 40 seconds. Now, anytime you hear about earthquake magnitudes or Richter magnitudes, it turns out there's a variety of different magnitudes that seismologists use. So if you look in different reference books, you'll see estimates ranging from 7.7 to 8.25 for the earthquake magnitude. Well, that could be due in part to the fact that different magnitude metrics are used. We'll talk briefly about how there can be a surface magnitude and a moment magnitude and other types of magnitudes as well. There were a number of deaths from the earthquake, and just a couple things to think about during an earthquake. It's not so much that the initial earthquake causes deaths, but it's more the aftermath. And in the case of San Francisco, the gas lines ruptured, as well as the water lines ruptured, so there were gas fires and no water to fight the fires with. And as a result of that, many people died. Now the death toll estimates vary widely, ranging from 700 to 3,000. And another thing to take into account is anytime there's an earthquake, there's almost certainly going to be aftershocks. So what happens is the initial earthquake causes damage in the structure, causes different types of cracking, for example. And the aftershocks, even though they're lesser magnitude, are also dangerous because that energy comes along and is base excitation for a structure that already has cracks in it from the main shock, and it could be that the aftershocks are what causes a given building to collapse due to pre-existing damage. So in terms of expense, this was the worst earthquake recorded in U.S. history. Now, in terms of magnitude, the worst earthquake in U.S. history was the 1964 Prince William Sound Alaskan earthquake. It happened on Good Friday, and these two photographs are from the Anchorage, city of Anchorage. You can see in the one on the left, the part of the street has collapsed, and it looks like these cars are now maybe about 10 feet or so below the street surface. And on the right-hand side, this was the famous J.C. Penney department store in Anchorage, and you can see it is partially collapsed. So again, this was the largest earthquake ever recorded in North American history. The duration estimates were from about 3 to 5 minutes long. Bruce Bolt lists it at 8.6 ms, where ms is the surface wave magnitude. And then the U.S. Geological Survey gives it a 9.2 MW, that's the moment magnitude. And if you want to learn more about how those magnitudes are defined, then you can consult a seismology textbook. In fact, Bruce Bolt has authored an earthquake book as well. The death toll was 131, and many of these, most of them occurred due to the tsunami effects that occurred. And in fact, some of those tsunami deaths, it wasn't just in the Anchorage area, but even places like California and Oregon were impacted by resulting tsunamis, and that causes a couple of deaths in each of those states as well. Okay, here's the 1994 Northridge Earthquake. This occurred at 4:30 a.m. on January 17, 1994. And this earthquake is notable for a number of reasons. Fortunately, it occurred at a very early morning hour, so the number of commuters on the freeways was less than at rush hour, and that's important because this earthquake was notable for different bridges and overpasses collapsing, and most of the deaths occurred, I think, due to this section of these various freeway sections failing. And the moment magnitude was 6.9. The duration was about 20 seconds. And this earthquake is also notable because it had the highest peak ground acceleration for the U.S. at 1.7 G. The death toll was 57 people. And another really interesting thing about this earthquake is it occurred along a previously unknown blind thrust fault close to the San Andreas Fault. So the San Andreas is the main fault that runs roughly along the coast of California, but there are a series of smaller faults that kind of are sort of crisscross or otherwise close by the San Andreas Fault. And it turns out that well, let me back up. A blind fault, such as the one associated with this Northridge earthquake, is not visible to the ground. So if you were in a helicopter hovering over this fault, you would not see it because the fault line does not reach the surface of the earth. It's underground, it's blind, it's hidden. And as a result of this, the U.S. Geological Survey did not know about this fault. And the local city planners and emergency personnel, the civil defense people, the hospitals, they did not know about this fault. Now certainly being in the Los Angeles basin and being somewhat close to the San Andreas Fault, they had to be prepared for earthquakes anyways, but they did not know about the specific fault that it could be the hypocenter, or you might say the epicenter for the earthquake. But other people did know about this fault, and here's what happened. At one time back in history, the Los Angeles basin was the richest oil-producing region in the world. That was years ago. And if you drive around the LA basin today on the various roads and freeways, you'll still see a few oil wells trying to churn out some oil, extract some oil, although just a relatively handful compared to once was. Well, it turns out that the oil companies had gone in and they have ways of doing seismic exploration. They will set off explosive charges on the ground and use geophones to monitor the resulting earthquake waves or seismic waves with the various reflections and refractions that occur. And they knew about this blind fault, but they consider it their proprietary data, and there are obviously different oil companies in competition one with another, and they kept that data to themselves. Well, in an ideal world, what they should have done is shared that publicly and made it public knowledge that yes, there are blind faults under the LA basin, and then the U.S. Geological Survey would have known, and the various civil defense and emergency personnel and city planners could have also made plans for a potential earthquake occurring due to this particular blind fault. Well, that's just sort of my little soapbox statement that we really ought to be more generous about sharing data with one another. Here's an interesting earthquake, the 2011 Virginia earthquake. So the previous earthquakes we talked about were the Pacific Coast earthquakes. But this one occurred on the East Coast. There was a particular town, a small town called Monroe, Virginia, and this is also called the Piedmont region. And that was the epicenter of this earthquake. And this occurred on August 23rd, 2011, 5.8 magnitude. And that magnitude was not nearly as severe as the previous earthquakes we looked at, but this earthquake is notable because it caused a 1-inch wide, 4-foot long crack to form at the very tip or near the tip of the Washington Monument. And the Washington Monument is a 555-foot high obelisk. And this monument is, roughly speaking, 90 miles away from the epicenter, which was near Monroe, Virginia. So even though it's kind of a moderate earthquake, and even though this structure, this historic monument, is 90 miles away, it still had some damage as a result of that quake. And the Washington Monument was closed for a number of years to the public, and I think it's now been reopened, and you could go online and find different images of the repair work, but basically the crack was filled in with cement, among other repairs. Here's an earthquake that's also notable, and it's called the Iwate-Miyagi Nairiku earthquake in Japan. This was not the big one that caused the Fukushima reactor problems, but this was one that happened at a different time in 2008, before the Fukushima-related earthquake. This one had a moment magnitude of 6.9 according to U.S. Geological Survey. And this earthquake is significant because it had the highest peak ground acceleration ever measured. And the 3-component value was at 4.36 Gs. So even though other earthquakes have had higher moment magnitudes, this one has caused the highest peak ground acceleration. Well, peak ground acceleration is measured at a point on the ground. And when we talk about the various Richter and other type of moment magnitudes, those are a measure of the total energy released by a quake over a large spread area. So the PGA, the peak ground acceleration, it depends on the soil conditions, the distance from the hypocenter, and other factors. And those factors combined to give this earthquake the highest ever peak ground acceleration. And that's all we have for today. So I hope you've enjoyed this unit, and that you'll make use of these SRS tools for your own work. And next unit, we're going to do pyrotechnic shock. So have a good day. Thank you, and goodbye.